Começando. Todos os participantes estão no modo somente escuta.
Thanks, everyone. Thank you for joining us for episode 15 in the Gleeble webinar series. I'll be your host today. My name is Dan Quigley. I'm the Director of Business Development and Marketing here at DSI. Some of you did join us for this webinar live at about 8 o'clock a.m. in New York time on Thursday morning. We did have some problems with technical difficulties. Your computer crashed at the wrong time, so we did have to cut that one short, and I do apologize for that. And we are re-recording this now, so hopefully everything will go smoothly this time. But again, want to apologize for that inconvenience, and we'll be sending this link out to everybody that was registered for the webinar. I think most everyone does agree that attending conferences in person is a great way to learn, network, and build collaborations. Unfortunately, at least here in the US, 2020 continues to get crazier and crazier. Based on the trends in the spread of the pandemic, we don't know when we'll be traveling internationally again. So since we can't attend conferences and see you all in person, we will continue to host webinars like these to connect and share the great work that is being conducted by the Gleeble community. We do talk a lot about the Gleeble community, but I do want to be clear that even if you don't have a Gleeble, you're certainly welcome to participate in these webinars, and we're glad you're here. We obviously hope to welcome you into the Gleeble community one day as a user. However, in the meantime, if you think your organization could benefit from Gleeble testing or simulation, please reach out to us. Our team at DSI can run tests for you. We do charge for that for contract testing, but we can also connect you with one of the organizations in your region that have developed Gleeble expertise in your industry or application. And we're happy to play matchmaker so that more real-world problems can be solved. As always, our goal will be to keep this webinar to 1 hour or less. Since this is a recording, we won't really do a Q&A, but if you do have questions for the presenter, please reach out to me. My email address is dan.quigley@gleeble.com, and I can connect you for those questions. So this will be an interesting presentation. Video of this presentation and all of our past webinars will be available online, and you can go see current webinars, past webinars. You can sign up for future webinars. Go to Gleeble.com, click on the resources link, and then scroll down and click on webinars, and that will bring you to a page really where you can see past webinars and sign up for new ones. Next week's webinar will be interesting. Dr. Peter Berezki from the University of Univaros will be presenting. Him and his team have developed some unique customizations, including a 3-point bending application with crack displacement and strain field tracking. So please do sign up for that webinar when you have a chance. But you're not here to listen to me. We want to get to the technical presentation. So today's webinar is a really interesting topic. Professor Julian Avila from Sao Paulo State University will discuss Gleeble work done in the Brazilian synchrotron light laboratory. He will also review some published works, and we'll talk briefly about plans for a new beamline at the recently built synchrotron source at LNLS. It's called Sirius. So Julian, thank you for your patience and coming back and re-recording this webinar. I'll hand this over to you now.
Okay, Dan, thank you very much. Thank you for all of you that try to attend the webinar early in the morning or in your time in your country. Sorry for the technical problem, that we are here ready for the presentation. Okay, I would like to start this presentation showing you this slide. This is the basic of X-ray diffraction. You have an X-ray beam coming to your sample. You are going to analyze a polycrystalline material, let's say, and you are going to get some diffracted beam, and then you are getting some data, diffractograms. You are going to measure X-ray phases using the X-ray or residual stresses. This is a conventional machine. You are going to find one in your lab, probably in the university or institute. But what about if we use the same concept, but we use as a source of X-ray synchrotron, and we use as a holder Gleeble machine? Okay, we are going to do the same exact experiment that you do in your lab, but you are going to do it with a higher energy source. Then you can get much more information in less time, and then you are going to use a Gleeble machine where you can perform different tests. You are going to heat your sample, you are going to apply deformation to your sample, or you can do both deformation and thermomechanical cycles. And then you are going to have also the diffractograms, but you are going to get diffractograms for every step in your test. That's why I'm here to tell you about, to describe some of my experience using this beamline that is called X-ray scattering and thermomechanical simulation, that is located here in Brazil. I had the opportunity to start working with this in 2016. I conduct some measurements in magnesium alloys. And last year we had the opportunity to test some steels. And yeah, this allows you to do different type of tests and get information, very important information from your material. And that's why I'm going to show you this presentation. Okay, let's continue. The outline of my presentation is this. I would like to introduce make some introduction, then describe the beamline, the XTMS, and I'm going to give you some examples from publication, from paper published using this beamline. And at the end of the presentation, I will show you some information about the Sirius, that is the new Brazilian synchrotron light source. And also I'm going to show you a photo of the molecule of the coronavirus. That's some of the things that synchrotron can use for. Okay, let's start. That's me. I'm not showing my video, but that's my photo, a recent photo. You can check my curriculum vitae and my resume here in this link. I have a short career as a professor and researcher, but there are some interesting information there. I'm highly interested in the additive manufacturing, welding and joining, and as a summary, the mechanical behavior of materials upon different industrial processing. This industrial processing can be additive manufacturing, joining, can be other processes. You know, you can transfer your material in different ways using different processes, and that's something that I am very interested. I have experience recently in additive manufacturing, mainly in laser powder bed fusion and wire arc additive manufacturing of metallic alloys mainly, and welding and joining, mainly using friction stir welding of high strength low alloy steels, aluminum and magnesium alloys. And also some experience doing material microstructural characterization using scanning electron microscopy, EBSD detectors, and X-ray, conventional X-ray. Also mechanical testing focused on fatigue, fracture toughness evaluation, and some experience conducting in situ test using X-ray coming from a synchrotron light source. I work for the São Paulo State University. It is located here in the state of São Paulo in the southwest of Brazil. And this university is a young university. It was created in 1966. The focus of this university is on regional development. And for that reason, we have 44 campi all around the state of São Paulo state, one in the capital in São Paulo city, and the other campi all around. I work here in São João da Boa Vista in this campus. Let's talk now about the XTMS, the beamline, some description. This synchrotron, the Synchrotron Light Laboratory, is located inside the National Center for Research in Energy and Materials. It is located here in Campinas, also in the state of São Paulo, in the southwest of the country. This is the synchrotron we used for a long time. This is the UVX synchrotron light source that it is currently deactivated because there is a new one called Sirius. And okay, we are going to talk about this, about the beamline that was installed here. But let's start for understanding how the synchrotron works. This is a representation of the synchrotron in a top view. You are seeing the rings, and you are going to start this process by creating electrons. You are going to produce some electrons. You are going to put those electrons in a ring, in a booster ring, let's say, and then you are going to accumulate some quantity, some amount of electrons during the day. And at some time of the day, you are going to inject those electrons in a bigger ring. This is called a storage ring. And then you are going to accelerate these electrons close or near to the speed of the light. And there are huge magnets to try to let's say to keep the electrons in a specific shape and doing this curve all the time, going around this ring. The magic of the synchrotron comes when you try to to change the trajectory of the electron, let's say like a tangent here. And then when you do that, you are going to use a bending magnet. You are going to extract this part of the electron, and then you are going to emit some radiation. It is called white radiation. That's the interesting part. That white radiation has different type of light. You have from infrared to ultraviolet, and also X-ray. That's why synchrotron is very important. You can use this energy to analyze cells, bacteria, virus, proteins, water molecules, or periodic crystalline materials, such metals, let's say. And it depends on what type of element are you going to analyze. You are going to choose a wavelength. A wavelength specific, in our case, to X-ray, we are going to work around these values. But let me come back. You are going to find some experimental stations all around the ring, here, 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 and all of them are going to be focused of the optics, are going to be focused in a specific wavelength. That's why you find biologists, physicians, a lot of different professionals working in a synchrotron, because it's a powerful tool. Okay, once we have the X-ray with a specific characteristics coming from the synchrotron, we got this beam. We put this incident beam in our sample. We generate some diffraction, and we collect that diffraction with a detector, put it here. Okay, that's different from the other Gleebles. You probably see that this chamber is different than the conventional chamber in a Gleeble, but the rest of the equipment is an Gleeble. So it's an Gleeble installed inside the synchrotron. And we are going to do the conventional test that a Gleeble do with the addition of the X-ray in situ diffraction. Okay, you can collect that information using a 1D detector or 2D detectors. It depends on what you want. The 2D detector, you are going to collect the dB square rings that give you much more information, but it's going to take much more time for each diffractogram or each part of information you are taking. Okay, let's go deeper. This is a chamber. This is the incident beam. You are going to put your sample here and the diffracted beam. And when you open the chamber, you are going to stand, let's say this is a duck bone. You are going to install this duck bone in the copper jaws here. And again, the incident beam is coming from here, and the diffracted beam is going out and is going to get collected by a detector. This is a closer representation of what happened with the diffraction phenomena. You have the white beam, the white radiation coming from the synchrotron. You use monochromators in order to choose only one wavelength. And for our case, we in this specific beamline, we use 12 keV. That's the energy. According with this graphic, you have the energy here and the wavelength here. We choose the energy of 12 keV, and we get this specific value of wavelength. Okay, so we set this monochromator in this wavelength. We have we know that we are only using this wavelength, a specific X-ray using that type of energy. And then we irradiate our sample, and we are going to produce the diffraction, and we have the detector here collecting all the information, moving in the 2 theta that you will know because you are going to set your experiment. Okay, that the same graphic coming from the monochromator beam. You are getting to your sample, and then you are diffracting that beam, and then you get information in your detector. The rest of the equipment is the same as a Gleeble. You have the jaws here. You can apply the load, or you can apply some heat, and then you can extract the information you want. It depends on your experiment. All of this is based on the Bragg's law. Probably you know about that, but let me explain something about it. You have a periodic structure that most of the metals has. You have some, for example, we have austenite and martensite here. We know that the space between atoms, this is this D space. It is known. For the martensite, you see that the D space between atoms is different in some cases. And that allows us to make math with those data, with that data. So we came with the incident beam. We are going to, this beam is going to interact with your sample, with the different planes of atoms. You are going to change the 2 theta, this theta, and then if you fulfill the requirements for this equation, that is the Bragg's equation, you are going to get some values. For example, you know the wavelength because you know the energy. You know the theta because you are you know how your incident beam is coming and how you are moving your detector. So you know the theta. As a result, you are going to get the D value. So you can get the diffractograms, and you are going to know very accurately the values between the atoms. So that's the main concept behind all of these beamline, all the X-ray phenomena. Okay, why do we use a synchrotron source for X-ray radiation? That's why that trouble doing experiments in a synchrotron. That's a good question, and the main difference is the flux of photons. You can have the same energy in a lab, in a normal equipment, and the synchrotron. However, the flux of photons is higher in a synchrotron. So that allows you to make fast measurements with high resolution. You are going to see much more details in shorter times. And as an example, I have here a 2 theta space, let's say between 20 to 120 degrees. You are going to conduct this measurement in a conventional diffractogrammeter, and there you are going to spend like 30 minutes. If you have on a high energy synchrotron, you are going to spend 5 minutes or less, probably less, 1 minute probably. And this is the difference. You can conduct in situ test. That's why it is important, and that's the main differences. The main difference. Other important thing is that you can reduce the size of your spot. You can go, depending on the synchrotron, you can go even to a window to 20 by 20 micrometers. That allows you to measure specific location in your sample. It is important if you have a weld and you are studying the heat affected zone, for example, but specifically within that region. That's amazing, let's say. Okay, you also have a smooth continuous spectrum. It means by using these monochromators, you are going to have a single wavelength, so you are going to filter very well your incoming signal, your incoming beam. Okay, this is for the experimentation. Let me take some water. During the experiment, you are going to have this detector here, and you have the incident beam coming to your sample, and then you are going to cause diffraction, and they're going to produce these diffuse star rings, and then you are getting photos in this detector. For this detector, for the size of the detector, in this beamline station, we are getting part of the diffuse star rings. Okay, you can, during the test, you can see the evolution of these rings. Some are going to appear, others disappear. And however, it is difficult to quantify things here. You need to transform these rings into diffractograms. So you do that for all the photos you get during your test, and then you are going to get the diffractograms. And after that, you are going to organize these diffractograms according to the order of your test. In this case, this is a study of Sousa Filho. The 2 theta or the diffractograms are in function of the engineering strength. And then let's focus on, for example, the austenite, this peak. In the beginning of the experiment, this peak is a big one. But when you are straining your material, you are making deformation of your material, plastic deformation, you can see that the austenite is, this peak is disappearing until you can't see really any peak. However, when you focus on the martensite, this martensite, prime martensite, you are going to see that it starts very small, and at the end is a large peak. So you can see that from this graph. You can say here that you're applying strain energy engineering strain, or you can apply heat, or both at the same time. And then you need to analyze that information and make some quantification. This is another example. We apply a heat treatments, isothermal heat treatments for 30 minutes. There are here 3 temperatures: 610, 650, 690. Okay, I'm only going to show you the last case, starting from the isothermal heating, from this point, from the high point when you reach the temperature, and then you are going to transform a complete martensite structure to austenite. So in that step, starting from here, you are going to have only austenite, all the 30 minutes. When you start the cooling, you are going to see that this austenite changes, the intensity is lower, and then it's just a shadow. It remains very little austenite. But when you transform this austenite, it becomes martensite, and then the peak of martensite is very intense. This is a top view. You have a range of diffractograms from here to the top, and it's basically another way to see the evolution. Okay, you can do the math with these peaks, with the diffractograms. We have several materials here: austenitic stainless steel, duplex, martensitic stainless steel, other carbon steel, and you can see the position of the peaks, austenite and ferrite, or martensite in some cases. And then you have this equation that gives you the volume fraction of the phases. You are going to have to discover some information about your material. but most of them is within these diffractograms. You need the intensity of the peaks, the weight of the peaks, information of the crystallography or the phase you are analyzing, and then doing that math, you are going to calculate the volume fraction. At least that's the tool we use. You can use different type of analysis to do this quantification. There are other groups using MAUT or doing other type of analysis. But in the end, it's probably the same. You're going to get close results. Okay, let's see what has been done with this XTMS beamline. As long as I have been following this project, there are 61 publications, including thesis, doctoral thesis, master's dissertations, conference papers, papers published in journals. Yeah, that's pretty much. We can see an increase in publication in the last years. Here in 2020, it's probably the more than 10 papers get published. I think so. There are a lot there were a lot of users. Probably they are going to publish this year. Okay. What did we achieve with this beamline? That's a good question. You have all the powerful tools of a normal Gleeble. However, you are getting information also by the X-ray in situ diffraction. So you can conduct heat treatments, thermomechanical or also mechanical deformation, compression, tensile or compression tests. And also you can conduct cryogenic and other type of tests that the normal Gleeble do. However, you are going to get information about the state of the planes of the matter during these experiments. There is something that we need to be aware of. I mean, you need to know, probably other presenters have talked about it. You need to be aware of your material. You need to know your material. You need to know how it behaves, where the transformation occur, or where the phases behave in one way or the other. Why that? Because you need to match your experiment with the data acquisition of the synchrotron. If you have a very fast phenomena happening in your material, probably you are not able to see this happening by X-ray diffraction. So you need to match the rate of your experiment, let's say strain heating or cooling, with the acquisition of your the X-ray acquisition of your material. It depends a lot in the state of your material. If you have a deformed material, it's going to have poor quality of diffractograms. But if you have a very crystalline material, it's easier to get high quality diffractograms. So you are going to play, you are going to test, you're going to spend some times. Probably you need to test before now, get some information about dilatation of your material, how the volume transformation is, and then you can move forward to use the X-ray facility. Okay, I'm going to show you some examples of thermal cycles and tensile and cryogenic right now. Let's start for the thermal cycles in high temperature. This is a study conducted by Fabio Faria Conde. He is a PhD at the São Paulo State University. No, on the São Paulo University of São Paulo, sorry. This paper was published in collaboration with a colleague in Portugal, João Oliveira. Okay, in this paper we use a marine steel manufactured by additive manufacturing, and we studied the kinetics of the austenite reversion. And then we produce the samples by additive manufacturing. We get these dog bone samples. We use it on the synchrotron, on the XTMS beamline, and we apply these 3 different isothermal treatments. And we can see here in this picture in the center the laser dilatometry getting by the Gleeble, by the sensor we have there. And here in the right y-axis, you can get the austenite volume fraction. And then you can see some information, but let's jump to the right picture. You can see here the austenite volume fraction and the time during the test. Let's go for the highest temperature, 690. We, on purpose, we use a really high heating rate in order to avoid all the transformation during that step. And then we transform all the material into austenite in few seconds, few milliseconds, and the material become austenite until we finish the test, this isothermal step. We see that let's say 100 of the material is austenite. When you cool down to room temperature, you get less than 10% of austenite. And now let's see for intermediate temperatures. We can see that we reverted, in this case, for the blue one, 70%. And we stabilized almost 70% of the austenite. So this austenite reverted in high temperature is very unstable and is going to change for martensite, but intermediate temperatures are going to work better. With this graph, we can design, or we can better design, for example, this reversion of austenite. I can choose a lower temperature in order to affect less my material, and I can choose a shorter time to produce, I don't know, 20% of austenite, let's say, and a stable 20% of austenite. So I can produce some amount of austenite in a specific time. Doing these tests, I'm able to say that, for example. That's very interesting. This is another study conducted by Dr. Julian Escobar. This study has a collaboration from different researchers from Brazil, the United States, Portugal, and Germany. In this work, he studied a super martensite stainless steel, and he conducted a similar test. He did the homogenization in the Gleeble, and then he applied some isothermal treatments. During these isothermal treatments, he used 2 temperatures above the TO temperature and 2 temperatures below this TO temperature. What does it mean, this TO temperature? It is where the Gibbs energy is similar between the martensite and austenite, and then if you go a little above of this TO temperature, you are going to revert the austenite. It's instantaneously, okay? And this is important to read the following photo here in the right. The isothermal, let's start from the right to the left, okay? You have the austenite volume fraction in the calculated or the measured in the left y-axis, and in the right y-axis you have the austenite in equilibrium calculated by thermocalc, and below you have the temperature. So you start your isothermal treatment here in the right, from the right to the left. So the isothermal treatment goes for the higher temperature until this point that reach the austenite, the equilibrium of the austenite. Calculated, it's perfect. For the other temperature as well, 650. However, for the lower temperature below TO, you can see that this equilibrium it wasn't reached. That's interesting. So the thermocal couldn't calculate this unstable behavior. But okay, that's one point. The other thing is that you can see that the martensite start temperature change from case to case, and then we can see a similar phenomena than the former paper I explained. You can see that even though you produce a lot of austenite during high temperature isothermal treatment, when you go down to room temperature, you are going to stabilize little amount of this austenite. That's very interesting. Let me say something. You can go and check these references. I'm just focusing on the synchrotron results, but you need to conduct a complete research complementary measurement like uh, microscopy, scanning, or transmission microscopy. It's needed. In this case, he used uh, atom probe tomography as well to see how the nickel evolved during the heat treatment. But it's a very good tool to see that, to correlate information. So I am just showing a part of the study, focus on the synchrotron. Okay, let's continue. Now let's see a nice example about mechanical testing. This mechanical testing was conducted in a high manganese steel, uh, conducted between researchers from Brazil and Germany. This is in a recent paper, I think was published last month, and it's very, very interesting. This is the result. Let's focus on the blue curve. This is in a conventional tensile curve. You have engineering stress in the left y axis, and in the x axis you have the engineering strain. Okay, in the blue you have all the deformation, the elastic deformation until the yield strength, and then you get the plastic deformation, isn't it? Okay, we know that. And now focus on, this is the information any tensile, universal tensile machine can give you. Now let's go to the in situ X-ray diffraction. When you reach this point, the yield strength, you are going to have, let's say 60% of austenite in this point, in this dashed line that corresponds to the yield strength. Okay, and now we have an epsilon martensite more than 35%, and we have less than 10% of alpha prime martensite. This is in this point when it reach the yield strength. However, when you start applying the plastic deformation, you are going to see that the austenite is changing, is transforming, is decreasing the amount during this process. Until the end, you get about 10% of austenite. And also the epsilon martensite is decreasing until you get below 10% of martensite. However, if we are reducing these two phases, we need to increase another one. What is this alpha prime martensite? You started with below 10%, and you are going up to 20 to 84%, let's say. So you transform this austenite and epsilon martensite to alpha prime martensite. And complete research, again, you can go to the paper and analyze all the beautiful picture they get, and they correlate this information of the synchrotron with the microstructure evolution. You can see a lot of green here corresponding to the austenite, and some part of epsilon martensite, a little quantity of alpha prime martensite. And then you can see the evolution coming this green, becoming yellow and red, more red. And in the end, you can see that most of the matrix has transformed to alpha prime martensite. This is a nice example that the things you can reach on this type of facilities. Okay, this is another example, thermomechanical cycles using cryogenic temperatures. This is an in-house development. Professor Osvaldo Cinto and all his group of research have developed a lot of different setup together with Leonardo Wu in this beamline in order to conduct this type of test in cryogenic temperature. This is an interesting result. They use an stainless steel, a 316L steel. And you have here the conventional engineering stress and strain curve, this black one here, for two cases in room temperature and minus 196 degrees Celsius. And now let's check the in situ information. You are getting here in room temperature ultimate strength of almost, let's say 600 megapascal and a strain of 60%. When you go to cryogenic temperatures, you are going to get almost double this value. You are going to get twice this value, and the strain is even larger than in room temperature. That's something very interesting. And then we can, using the X-ray diffraction, we can see how these phases transform from austenite to martensite. And just for comparison, we have this point where the martensite is 50% and the strain is almost 60%. However, in low temperature, that same crossing point is going to happen in a strain of 0.13. There are much more information in the paper. I invite you to check those papers and see why this is happening. I'm not going to explain it here, but that's something that you can see while is conducting the test. Okay, for the thermomechanical test, we have this work. It's very interesting, conducted by Fulvio, that is a researcher, a doctor working for Gleeble, and Claudio Aranas from Canada, and other researchers from the United States. In this work, they use a conventional carbon steel, and they apply several thermomechanical treatments. Let's say they are going to step from step, going from the biphase field, and then they go to the austenite field. They go to a high temperature, simulating the rolling process of a steel plate, and then they get an X-ray diffraction. Here in this step, they make a deformation, get some diffractogram here. After 5 seconds, they conduct the other diffractogram after the deformation, and 9 seconds after that deformation, they get another diffractogram. What is interesting here, when you conduct the deformation in that austenite field, you are going to see some ferrite appearing. So what is the conclusion of that? That while you apply deformation in that field, you are going to create ferrite. Just as after 5 seconds, you can see barely a small peak of ferrite. And after 9 seconds, all the evidence of an existing ferrite has disappeared. So that's the main point of this. You can then produce a material with some ferrite within your material. I don't know why, or if it is useful or not. Or you can also avoid the formation of austenite if it is deleterious for your material. Anyway, you can use, as shown here, you can use this type of facilities to better develop your processes in the industry. Okay, just this is the last part. I'm going to talk about the plans. We have some researchers about the about a beamline that we have a project that we have the necessity for a high energy X-ray diffraction beamline focus on material science. And the idea is to get a beamline here in the series synchrotron. This is the photo. This is a recent photo of this series. This is the new Brazilian synchrotron light source. It is called Sirius because it's the brightest star in the night sky. This is a fourth generation synchrotron light source, and it was designed to be the brightest synchrotron in this generation. And as I promised, I can show you here, this is the holder of a sample of a molecule, a protein of the COVID virus. And then you put this sample within the experimental station, and then they get this image of the protein of the coronavirus. This is just an example, the things you can do, the important things you can develop using synchrotron light source. Okay, we gathered some researchers from different countries, Brazil, Argentina, Colombia, Chile, Portugal, US, and Netherlands, most of them from Brazil. We conducted a survey to know what were the necessities for conducting experimental tests, in situ experimental tests in the synchrotron focus on material science. We got that results. We transformed those results on some technical specification, and this is the list. We need a high energy beam in order to conduct different type of tests, mainly to work in transmission mode to get much more information of the material. We also need a machine capable of performing different tests. We thought about the Gleeble because you can use the Gleeble to make to conduct tensile, compressive, torsional, bending, and other type of tests, and also applying heat. And other options can be to use a fatigue machine or an only tensile machine to make the tensile test, as well as the compressive compression test. Okay, we are discussing this. We are an independent group. We are researchers from other institutions. We don't work for this center, but we are requesting, we gather, and we are requesting a beamline with these characteristics. If you're interested in this project, you want to use these facilities, and you want to make part of this request, you can write us an email to me, and I can show you the complete project we have. And yeah, sadly, we have in a difficult time in Brazil. The economy it's complicated now, but I hope in some years we can have this facility running. Okay, anyway, we need also a high resolution dilatometer. That can be another element. High resolution sample holder. Let's say you have a big part, and then you want to measure the residual stresses in different places. You need to a holder that is capable to move that sample very fast in an accurate way in order to position the beam in specific places of your sample. Also, we need a small beam, the ability to reduce the size of the beam in order to analyze thin films. Probably, yeah, we are discussing. Probably it is not, I don't know if it is possible or not. An ultra-fast acquisition area detector in order to get to see phenomena happening in high rates. Okay, this is an scheme of the experimental station. It was conducted for a colleague, Guilherme, Dr. Guilherme, and we have here in this left part there is a synchrotron producing the X-ray diffraction. We have all the optics that's going to adapt the beam to the X-ray characteristics, and then we have the X-ray coming from our sample. Our sample can be installed here in the Gleeble, or can be installed here in the generalized sample environment. What does it mean? It can be a tensile machine, fatigue machine, and furnace, and any type of different equipment we need to conduct our experiments. And here is the place where we are going to put our detector. It can move depending on the material and the test. We are going to move this detector. This is our first approach to this project. We have had some meetings with the Center of Research in Campinas. We are just waiting for better news of the economy, or some companies to fund this project. There are some companies interested. However, I'm not going to mention the name here. Anyway, if you're interested, you can send me an email. I would like to thank all of these researchers and students that has used and have been using. For example, Antonio Ramirez was one of the professors or researchers at the time in charge of developing this beamline together with Leonardo Vu and Guilherme at the time. And yeah, all these people, thank you very much for installed, develop things, and introduce me to this new way to analyze materials. New way for me, this technique is not new, but in the way we are using it, it is new. I think it was the only Gleeble machine installed in a synchrotron all around the world. Okay, I would like also to thank this institution, São Paulo State University, the Light National Synchrotron Laboratory, the São Paulo University, and this funding institution, FAPESP, CNPq, and CAPES. Okay, and before we finish, I would like to tell you that conducting these X-ray diffraction experiments, it's fun. We go with the students and we spend like 3 to 5 days, 24 hours. We divide the groups in teams in order to do all the experiments. Sometimes you are happy, sometimes not much, but in a summer you are going to discover nice things and enjoy the time there. Okay, thank you very much for your attention. As Dan said, you can send me an email with the question or contact directly the Gleeble team in order to solve your questions. Okay, this is some source of information. I can share with you this presentation and then you can check the information anytime.
Great, thank you, Julian. This was a great presentation. Appreciate you putting that together. It does look like running those tests can be fun. I'm surprised it's that many days, hours straight. So that's impressive. Thanks again also for making this presentation again and recording it for us. I think people will appreciate being able to watch this whenever they can. I will also share your email address with attendees in a follow-up email that will go out to people. And if they do have questions, since we don't have Q&A live, hopefully they can email you if they have questions directly. If anybody out there has questions about Gleeble and need some support from our team, I mention this at every webinar, but I do encourage people to go to the new service portal that we have on our website. Gleeble users can register there and then access a knowledge base as well as create support tickets, which is very helpful, especially when our service team is traveling all over the world. They're not traveling right now, but hopefully they will be soon. And then instead of emailing a service engineer directly that may be on an airplane or traveling for days, it's best to create that support ticket, and our team can then direct that to a resource that is in-house and ready to support you. Again, thanks everyone for your attention. I appreciate it. Hope everyone stays safe and healthy. Anybody has any questions, please do feel free to email me directly, dan.quigley@gleeble.com. Have a great day.